Okay, people. So yesterday we were talking about semaphores, and we said that semaphores are actually very simple structures. They are supported usually by operating system. You may think semaphore as like integers, special kind of integers. You can do two things on a semaphore. You can either increment this integer or decrement it. Down operation and up operation. Okay. Down operation decrements the integer by 1 if it is not 0. If it is 0, it cannot decrement it. So what does it do? It blocks the calling process. It says that, okay, I am going to block you until this integer, this semaphore becomes non-zero. Somebody increments it. Okay. So you wait until the semaphore becomes non-zero, and when it becomes non-zero, 1 or some other value, and it continues and it decrements it by 1, and it gives it returns back from this function. Up just does kind of the opposite. It always increments the integer, the semaphore, by 1. Only in one case, if you are incrementing a semaphore and if its value is 0, then that means that maybe somebody is waiting on it because somebody is trying to down it, and so maybe I should wake up somebody. So up never blocks, down blocks from time to time. Okay, so that's as easy as this. And we said that let's see how we can use this semaphore idea for our producer-consumer problem. Okay, usually we use it this way. We define a semaphore, think it like an integer. Okay, and if I initialize this semaphore, mutually exclusive region, semaphore MEX is obviously the name of the semaphore here, as 1. So when I say down this MEX, I can enter my critical region. If it is 1, then I can decrement it and it will continue. If it is 0, then that means that somebody is using this critical region. I cannot enter this critical region. I have to wait until it becomes non-zero. Okay. So if it is 1, then I decrement it. I enter the critical region, and when I leave the critical region, I increment this value by 1. So it becomes 1 again. It is not 0. Okay, so that's the idea. Here, our critical region, entering the critical region and leaving the critical region becomes as simple as this: down it and up it. Okay, decrement and increment and decrement it. Down can block from time to time. Up never blocks, but up has something to do different from down. It may wake up some of the process waiting for this semaphore. Okay, so let's see this in an example on our producer-consumer problem. Okay, we have a buffer of 100. Okay, 100 empty buffers, and at the beginning, and I have a producer and I have a consumer. They work like this. Okay, so in an infinite loop, producer produces an item, inserts it and produces it, inserts it and produces it. Consumer removes the item from the buffer and consumes it. As I said yesterday, it's like a print spooler. Consumer is the printer daemon. It checks the buffer. If there are any files, it prints it. Producers are any processes that are sending files to be printed. You may think it like that. Okay, so I produced an item and I decremented this empty semaphore by 1. Okay, so I am going to use 3 semaphores, 1, 2, 3. The reason why we are using 3 will be clear in a few minutes. Okay, so at the beginning, since empty is n, n is 100, by the way, here. Okay, since empty is 100, I can decrement it by 1, no problems, because it is a non-zero value, no problem. So I will decrement it by 1. Then I will come to this mutually exclusive region, the critical region. Can I enter the critical region? And since mutex is 1 at the beginning, I can of course decrement it. And I will insert my item to the buffer in an exclusive way. Nobody can be in this region while I am in there. I inserted it, then I increment this mutex by 1, and I increment it, after that, see, I am doing this up full by 1. What does that mean? It means that I am incrementing the value of full, which is a semaphore, which is an integer, by 1. Why? Because I have inserted one element to the buffer, so the buffer has one less available space. I used up one of the available spaces in my buffer. So I am decrementing empty by 1 and incrementing full by 1. Okay, this is what the producer do. Let's forget about the producer. Let's run the consumer at the beginning. Let's say I never run the producer at the beginning. I am running the consumer. Consumer says that I am going to decrement full by 1 at the beginning. Okay, well, full is 0. I cannot decrement it. So what is the behavior of semaphore? Semaphore says that I cannot decrement it. I am going to block you, and I am going to wait until full becomes non-zero. Okay, so this will be blocked. Consumer will be blocked at the beginning if it runs first at this position. It will wait until producer makes this full and non-zero value, right? Okay, so that's the reason why we are using this empty and full for two semaphores. Okay, empty shows us the number of available spaces in my buffer. Full shows me the number of available spaces in my buffer. Sorry, did I say it correctly? Okay, so this one, full measures this amount, empty measures this amount. Okay, at the beginning empty is 100, full is 0. It is always empty plus full is always 100. Okay, so for a producer to be able to enter this region, you have to have some empty spaces, right? The empty should be different from 0. It should be greater than 0. For a consumer to enter this region, full has to be greater than 0. And likewise, the consumer, if it enters this region, it says that, okay, I enter the region, I need this mutex, okay, I need this critical region guard. This is the critical region guard mutex. I down it, and I remove my item, and I say that I am out of the critical region. Now I have consumed one item from the buffer. There is one space available, one more space available. I am incrementing the empty by 1, and I am consuming the item. Okay, good. So basically, we are doing this producer consumer with semaphores. Well, we are doing more than this critical region thing. Previously, we were doing the critical region thing. Okay, if I am in the critical region, nobody can be in the critical region. We are doing two things at the same time here. Okay, this one satisfies the critical region rules. Okay, race condition rules. The other one, okay, very efficiently solves this problem of sharing a buffer. Okay, if I have enough space in my buffer and etc. If I had a buffer of just 1, actually, maybe one single semaphore would have been enough for this problem. But I have a buffer of 100 size of 100. Then I have developed this clever solution. It's very simple and it's implementable. It doesn't have any race conditions. I can handle everything very nicely. Okay, but I needed 3 semaphores in this case. I mean, in this case, I have 1, 2, 3, 4 system calls here and 4 system calls in this simple loop. I am getting lots of help from the operating system. So there are 2 places where I can be blocked. I can be blocked if there is no enough space in my buffer here, or I can be blocked at this position with the mutex. Okay, any questions? Did you start the attendance? Okay. You are not signing for other people, right? That would be a bad thing. Okay. So I question for you. What happens if I remove this line, this line, this line, and this line? So I am saying that let's not use this mutex, this binary semaphore. Well, I can be already blocked here, and I can be blocked here. It kind of satisfies both the constraints of the available buffer and the critical region thing, right? Am I safe? Why not? Why not? You said this, right? This means no.
Because inserting item and removing the item requires also.
I did not understand anything what you.
Because inserting an item and removing an item also requires a critical reach. I mean, they
Why?
share the same buffer.
We are using the same buffer, yeah. So you are saying that you cannot be inserting an item and removing the item at the same time, right? It cannot happen. So I should prevent it. And this down empty and down full doesn't, they don't do this, because let's say if empty is 50 and full is 50, they can both enter this region and that region, okay? So this guards and this one guards if the buffer is empty or full, it checks those numbers. But this mutex, this binary semaphore, we call it a binary semaphore, okay? Binary semaphore actually satisfies the rules for the critical region. No two processes can be in the critical region at the same time. So, okay? This is about the critical regions, and these are about, do I have enough space in my buffer? Okay, do I have enough space in my buffer? Okay, maybe you could have done this. You could have, okay, eliminate these two. Okay, eliminate these two, empty and full. And inside this critical region, maybe you would say that, okay, do I have enough space? If I don't, then I'm going to run into a spin lock. And you can run into a spin lock, and spin lock will run this empty loop until the buffer is available. Maybe you could do that, but you know the problems with the spin locks, right? They are inefficient. I don't like it. So this one is both efficient and it elegantly solves the problem. Good. So did I miss everything? So implementing semaphores is done typically in kernel. We talked about this. So you make a system call for the semaphores. You say that decrement this value by 1. And if it is 0, then block. Or increment it by 1. If somebody is waiting on it, then wake them up. Okay. And while this semaphore is implemented, because I mean this incrementing and decrementing, making this calling thing is has to be done in an atomic way. So it is up to the kernel whatever it needs to do. So usually it masks the interrupts, because it is a kernel. It can do whatever it wants. Okay. So on multiprocessors, maybe for multiprocessors, maybe, I mean, masking the interrupts is not enough, because if I have more than one processor, then that's going to be a problem. Why don't you use set and lock TSL instructions? Okay, and since both of these instructions take a few microseconds, and I don't do these kind of operations very often, we don't get very large penalties for executing these kind of instructions or these kind of system calls. Okay, good. So I like to differentiate between these two semaphores and this one. This one is called a binary semaphore. This is intended to be used like a guard to enter a critical region. It can be either 1 or 0. These are different. Okay, it can be either 1 or 0. These are called mutexes. Okay. These are called mutexes. And mutual exclusion semaphores make sure only one process is in the critical region. Okay. So in this case, in our case, it protects access to the buffer. So where do we use this? We use this as regards to our critical regions. Okay, and the book says that maybe I should put this down mutex and up mutex inside this insert item function. So insert item function calls down mutex, and when it is done, it calls up mutex. So maybe these three should make a function. Okay, function insert. So that will be clearer, much more clearer. Maybe the book says it that way. And again, maybe these three should be remove item function. Okay, so that's a special semaphore. It's a binary semaphore. The others are counting semaphores. Okay, it's an atomic way to manipulate a counter with blocking F0. Atomic way, I carefully say it's atomic way because you cannot have a switch while you are decrementing it and making a call and doing that kind of stuff, right? So it's an atomic way to manipulate the counter, and the operating system guarantees that it is done in an atomic way. Okay, and we use these kind of semaphores for synchronization between the processes. Synchronization is this. Okay, obviously these two depend on each other, and these using the semaphores I synchronize them. Okay, they communicate that way, and if the buffer is empty, consumer cannot continue. If the buffer is full, producer cannot continue them. They have to communicate. They have to synchronize this information between them. And counting semaphores are a good way of satisfying these kind of conditions. Of course, in this case, I was very clever. I designed my system in a way that, okay, remember, I can block on empty or full if they are zero only. Semaphores work that way. You cannot say that if full becomes n, then block. There is no way to say that in a semaphore, okay? Semaphore only blocks if the value is zero. Okay, there is only one condition. So you have to change your algorithm slightly so you have such a variable that reaches down to zero when it needs to be blocked. If you cannot design your system like this, then maybe your semaphores are not exactly the thing that you wanted to use. Maybe you should do something else. For example, in that case, you like to block if n is a power of 2 for some reason. I don't know, maybe if n is a power of 2, then you like to block for some reason, then this semaphore will not work, right? It will not work. There are other ways of achieving this, and we are going to see it in a few minutes. Okay, good. So mutexes are binary semaphores. Okay, they are a special case of a semaphore, and they are useful when no counting is needed. Only a bit is enough. You don't need much memory for that. And using the TSL instruction set, it is TSL instruction. It is easily can be implemented. Okay, you try to grab the lock. If the lock is there, then you just grab it. Otherwise, you block. Okay, and let me show you the implementation of this mutex using standard TSL instruction. Okay, so to enter a critical region, you call this function. To leave the critical region, you call this function. Let's look at the. Okay, let's look at the leaving the critical region. You just move a 0 to variable named mutex. Okay, I have a global variable somewhere in my address space. Name is mutex. So make it 0. 0 means that the lock is available. Okay, so whoever wants to enter this region can enter it. So let's see what kind of procedures we have inside lock. So TSL, remember what the TSL do? Okay, what the TSL does? It moves the value of mutex to this register, and it moves a 1 to this mutex. Okay, and it does this in an atomic way. There cannot be any interrupts or any other stuff happening while this is being done. It is done in an atomic way. So I move mutex to register and I move on to mutex. Since I am trying to enter the critical region, I will enter the critical region if mutex is 0. Okay. After this, I do this comparison. Compare the register with 0. If the result is yeah, they are all equal, then I can enter the critical region. So if they are equal, if the register's value is 0, that means that the initial value of mutex is 0. I can enter the critical region. Otherwise, if they are not equal, that means that somebody had the lock before, so the value of mutex was non-zero. So that means that I am going to block myself. Okay, I am going to call thread yield. I am saying that, well, there are other threads working with me. We are cooperating with each other. And I am going to wait until somebody else makes this mutex available for me. Somebody else is going to make this mutex 0. Okay, so I block myself. When the time comes, the thread scheduler will let me run again. When I am running again, I will immediately jump to the beginning of the loop and I will run this TSL again. If this time I am successful, then I am going to return and I will enter the critical region. So this is how you implement mutexes. Okay, this is how you implement the mutexes. Well, it looks like you don't need any. It looks like you don't need any kernel privilege to compile this code. TSL is not a privileged instruction. I can do that. So that means that I can have a thread library running this mutex lock in the user mode, which is nice because I don't need the kernel. Well, the only thing is that sometimes I need to call this thread yield, and if my thread library is in the kernel, then it's a system call, right? Good. So that's as easy as this. So it is implemented using the TSL instruction. Of course, this assumes that I have this TSL instruction available on my hardware. Good. Any questions? Yes.
Where does thread yield come from? Do I have to implement it or?
Where does the thread come from?
Thread yield is called thread yield.
What again?
Thread yield.
What do you mean? Where does it come from? It's a system call.
It's system call.
Yeah.
Okay.
Remember threads? There is a function thread yield, create thread, and destroy thread and thread yield. Thread yield means that I am going to let the operating system take the CPU from me. I don't need the CPU for now. I am going to sleep. So I am helping the other threads to do. I mean, instead of this, right? I can immediately jump to mutex lock. Okay, I can immediately jump to mutex lock. Instead of doing that, okay, just take this out, and this will work too, but this will make a spin lock. Okay, and an infinite loop, a spin lock, and we don't like this because this is very inefficient. So, but if I yield my CPU, then everybody would be happy. Anybody else? Okay, let me continue in that case. Okay, so these are all talking about, okay, using the common address space to have this communication, because we are all, for example, if I am doing this, okay, producer and consumer, both of them have access to this number, and this number, right? I mean, these are all global variables. I am sharing them between those, and this is possible with the threads. That's the idea of the threads. But how about if this is not possible? How about if I am doing this with the processes, different processes? Okay, if I have two processes with disjoint address spaces, how can I use the semaphores or a common buffer? Okay, well, in that case, everything has to be implemented by the kernel. Okay, everything has to be implemented by the kernel, and kernel has its own space. When you say, okay, first of all, you ask the operating system, give me a semaphore. Okay, the operating system says that, okay, here's your semaphore. So operating system allocates space for that integer for that semaphore. Okay, and if somebody else using the same semaphore, you end up using the same space in the kernel area, kernel memory area. Okay, that's one thing. The other thing is that different processes doesn't always mean that they have disjoint address spaces. You may ask your operating system to share some of your address space with the other processes. And when we come to the virtual memory, the chapter number 3, okay, in that chapter we are going to see that this is very conveniently done using the paging mechanism. You will say that, let's say, I have pages of memory, let's say 50 pages, and I am sharing 2 of these pages with the other processes. And this is very efficiently done with the help of the hardware, and this is possible too. Okay? So usually either you share your space in the kernel area, in a controlled way, of course, or you share your memory space with the other processes using paging or segmentation. Good. So no problems. I mean, you might think that these are all valid for the threads, not the processes. No, these ideas are all possible for the multiprocesses too. Okay, some people say this. Okay, let's look at this one. I checked if the mutex is available. It is not available. Then I immediately called thread yield. Let's say my thread library is implemented at the kernel level. This is a system call. System calls are expensive, context switch time, right? So as soon as I figured out that the lock is not available, that's going to cost me some time, okay? I don't like this idea. Maybe I should try this a few times, right? Run this loop for a few, maybe milliseconds, okay? If still I don't get the lock, then maybe I should yield. That's the idea. Maybe this is a smarter solution. So don't just give up with just one try. Try it a few times, a few milliseconds, half a millisecond, whatever. If the lock is not available, then block yourself. Because, I mean, what am I going to do inside my critical region? Only a few instructions, right? So whoever is holding this lock, they will be done in a few milliseconds, microseconds, whatever. Okay? So maybe I should just be patient a little bit. If it still doesn't work, then I should yield. So this technique is called fast user space mutex. So I am kind of delaying my system call, okay, until it is available. But if it is taking too long to get the lock, then I am going to block, okay. Block only if necessary and switch to kernel space. Okay, so I'm not going to talk much about this, but these kind of hybrid solutions are available. Good. And I think when I showed you do I have this Mutex library? I think I had yeah, this is a problem here. We talked about this producer-consumer problem with race condition. This code didn't have anything about synchronization. This was just a straightforward code. It doesn't talk about the insertion and the consumption of the item, no critical regions, no buffer, etc. So this is not good, but it looks like no. Yeah, I didn't tell you anything about the pthread library support for. Yeah, okay, here it is. I found it. Okay, so pthreads for the mutexes. Okay, to create a mutex, you call this function. To destroy a mutex, you call this function. Okay, to get the mutex, you call this function. To release a mutex, you call this function. And this is a special function. See this one? You try lock. Okay, you get the lock. Once you get the lock, you get the lock. You can enter the critical region. If you don't get the lock, this one will return. It will not block, and it will tell you that I didn't get the lock. This one will always get the lock. Okay, it will either block or will get the lock. Well, at the end of blocking, it will be unblocked, and so you're going to get the lock, right? So this one, when you call it, you will get the lock one way or the other, maybe after a long wait. But this one will immediately return. Either you get the lock, or it will say that, okay, I'm returning -1, you didn't get the lock. So do whatever you want. You don't get the lock, maybe you want to do something else. Maybe you are going to run into a spin lock. Maybe you will do something useful else. Okay, maybe you try to solve this problem in somewhere else. So this is try lock, and that's what I am talking about here with the. Okay, I am solving this problem. In the user space using this mechanism, fast user space mutex. Try lock. Okay. Great. Okay, so so far we like this idea of, at least I like the idea of semaphores and the binary semaphores. They are nice. They block when the things are not available, but they only block when that integer becomes 0. Sometimes my life is more complicated. I like the block if I meet some kind of a condition, okay? If I say that if n becomes this, if this string becomes this, then block and etc. How am I going to do that? For that, they have invented this idea of condition variables. Okay? With the condition variables, you can specify any condition that you like, because you are going to say that, okay, I am blocking myself. This happened, and I am going to block myself. And they are usually almost exclusively used with the mutexes, because mutexes are good for the critical regions. Condition variables are good for the blocking if some condition is satisfied or not satisfied, like our producer-consumer problem. I like the block if the buffer is full for the producer. Also, I like the block if the mutex is not available, right? So I am going to change this first part. I like the block if the buffer is full with this condition variable, just to show you how this thing works. And the mutex part will stay the same. And I'm going to show you how it is done with the Preemptive library. Okay, so almost always the two methods, okay, condition variables and the mutexes are used together. Let me show you this. Okay, so these are the stuff for creating a condition. Okay, creating a condition variable, destroying a condition variable. This is the thing that I am talking about, wait and signal. When you call this function pthread condition wait, it means that I am going to block myself, something happened. Okay, and condition signal means that if somebody is waiting for me to unblock them, then I am signaling them. Yeah, whatever you are waiting for, okay, is available, take it. Okay, and broadcast is used for if many people are waiting for me to do something. Yeah, I did that, and wake them all up. Okay, so let's look at the code again. This is producer-consumer problem written in C. Let's look at, okay, I have three functions: producer function, consumer function, and my main function. Okay, and I have this not infinite loop but very large loop, and these are my variables. I have a mutex, the mutex, and I have two condition variables, one condition variable for the consumer, the other condition variable for the producer. Consumer is very concerned about if the buffer is empty. If the buffer is empty, it cannot continue. Producer is concerned about if the buffer is full, I cannot continue. Right, two condition variables. Okay, and my buffer is the place where I place my produced item, etc. So, producer and consumer. Let's look at the main function first, maybe. Main function says this, okay? I have two threads, producer and consumer threads. I have a mutex. I am initializing it this way. I have two condition variables. I initialize them using this function, condition in it. And now I am letting two threads run now. One of the threads will run this function consumer. The other one is the producer. And I will wait until both of them are done. After that, I am going to destroy my condition variables. Also, I am going to destroy my mutex. Okay, so that's the main function. So when the main function calls these two functions, consumer and producer, they immediately start running. So I will have three threads at this point. In this process, I will have three threads. One of them is the main thread. It's still running. The second one is the consumer thread, and the third one is the producer thread. And the interesting stuff is happening between these two consumer-producer threads. Okay, let's look at those two functions. This is producer. Okay. I didn't send any data to this producer, right? Did I send anything? No, it is 0. It is all null. Yeah. Okay. So producer says that I have a loop from 1 to max, very large number. Okay. So before I produce anything, I need to be in the critical region. This is the entrance of the critical region. This is the exit of the critical region. Okay. Because I am trying to get the lock. So I might be blocked at this line. Okay. Because consumer is going to do the same thing here too. It will try to get the lock at the beginning, and it will try to, it will release the lock here. Okay. So this is the critical region for both of them. So only one can be in their critical region, not both of them in the critical region. Let's look at this. Let's look at this inside the critical region for the producer. It says that if buffer is not 0, well, buffer is not 0 means that I have produced something, I put it in there. Okay, this is how you put your, well, I mean, this is a very simple example. Producing something in this case is putting this number I, this I, into this buffer. So I produce this integer, okay, just to keep the thing simple. I mean, usually, let's go back to our classical example of producer-consumer thing. I produced a file. I am putting this file in this buffer. I'm expecting a consumer, a printer daemon, take this file and print it out. Okay? But in this case, let's keep the thing simple. I am going to put this I into this buffer. So I say that I am checking if the buffer is not 0. If the buffer is not 0, that means that there is some data to be consumed in there. I cannot put my data in there. So I will, what am I going to do? If buffer is not 0, I will run this while loop, and this while loop says that, wait, block yourself, because pthread condition wait, okay? I am going to block myself on this condition of this producer, condition variable of producer. And I am going to wait until somebody wakes me up. Who is going to wake me up? Okay, this consumer, when it consumes the data, it's going to tell me that pthread condition signal condition producer condition p. So I am going to wait until somebody wakes me up because the buffer is not empty. A buffer is not 0 here in this case. Okay. So I am waiting for this condition to be happening. Remember what we did before with the semaphores? We said that decrement this variable by 1. If it is 0, then block me. In that case, the condition was about that number being 0 or not. In this case, well, I am checking the condition myself. Well, I mean, it is almost the same thing, a buffer is 0 or not, but I mean, I can put any if statements I like in this place, right? So I am making the decision myself. I am blocking myself because I have seen something is happening, I cannot continue. Okay? P thread, condition wait, and con P. Okay? Well, interestingly, there is a second parameter on this. Well, okay, let me put a red mark around this one and red mark around this one. Don't let me forget about it. We will talk about that. That's important. Okay, let's ignore that for a while. So basically, this line says that, okay, block me if the producer condition is not met, and this is in a while loop. Why is this in a while loop? Why this is not? Why this is not an if? Can anybody tell me? Well, I mean, if would have been enough, right? Yeah?
There may be more than one consumer. Other consumer may be consumed, so there is no product.
Yeah, that might be one explanation. I mean, what happens if there are many producers and one of them took the buffer and filled it in? We don't know. It is safer to put a while in there, because the fact that I woke up doesn't mean that the buffer is available, right? It may not mean that the buffer is available. I woke up and I am in a while loop. I am checking the buffer again. If buffer is not 0, then I am going to sleep again, right? So it's a better idea to put this in a while loop. Okay, so I wake up for some reason. Somebody woke me up, and I am checking if the conditions are right for me to continue. If buffer is not 0, then I will sleep again. I will block again, and then I am in the critical region. I assign this value I to my buffer, and then after that I am done. I am saying that if anybody is waiting for this condition C, consumer condition, to be satisfied, then let them know that there is some data inside the buffer. Okay, so I am signaling this condition variable, and guess what? Who is waiting for that one? The consumer is waiting it. If the buffer is 0, that means that there is nothing to consume. I am going to wait until this happens, and when this happens, this can wake up and it can continue. Okay, so I can block at this line for the producer. I can block at this line for the this one for the producer, for the consumer, and this one plays nice. It says that if anybody is waiting, then let them wake up, and this one says that if anybody is waiting to fill the buffer, let them wake up here. And of course, when you leave your critical region, you release your lock. Good. So this is the condition variable. If you ask me what did we do more compared to this semaphore version of the same program, is it this one? Semaphore version of the same thing. That this thing is stupid. I forgot to update it. Anyway, I don't have to show it. You remember the thing, but I am okay. It looks like I am losing my. Okay, let's take 10-15 minutes of break, and when we come back, I will ask the same question. What did we do more compared to the original semaphore version of the program? The answer is nothing. We did exactly the same thing. Previously, we were relying on the semaphore being 0 to block. Now we are making this decision ourselves. So that was the answer. Okay, let's get 15 minutes of break. Let's be here around 11:32. Şimdi anladım böyle montla oturuyorsunuz. Böyle çok daha sıcak ya. 3 saat bile daha anlatırım ben bunu. Dün dondurdunuz beni burada. Geldiysen yok olmadığı zaman atarım. Gelmediği zaman olmadı. Tek kırılıyor.
Ondan sonra bir konuşmaları bekliyorum. Tamam mı? Mutexes şimdi yani bu şeyi burada biliyorsun. Bu demek ki ayakta da almak yaptı ya bu için. O zaman bu buraya girecek. Sinyal yolladığı zaman bu yanlış falan.
Çalışır ama.
Yok hayır. Sinyal verdiğin zaman tamam işte hayır o yüzden.
Hayır,
O yüzden bak.
hayır, vallahi.
Dur. Sinyal veriyor tamam mı? Bu sinyal verdikten sonra bu uyanmaması lazım. Niye uyanmaması lazım?
Blockchain içeride kritik değil zaten.
Şunu yapıyor oğlum ya. Loka aldı ya. Unlockladı. Loka aldı. Hala locklu. Hala locklu. Baktı buna. Uyumasını konusunda
Anladın mı?
Dur. Abi bunun için diyor. Nasıl bakıyorsun? Bir de bakıyorsun nasıl?
Bu değil. Bu bakıyorsun. O çalıştı, o kıymetli. Mesela sizin gibi aslında bu kıymet olmayabilir. Yani ne üretici bu kızlar?
İkile baksana. He, arada başka biri üretirse
Boşuna bu.
ben iki kişi ürettim.
İki üretiyorsa sıkıntı ya.
İki kişi üretirse ne yapacak? Bu produce.
Ya,
Şunu anlamadım. Şimdi burada var. Biz sıfır değil uyuyoruz. Bu geldi. Bir olan. Sonra iki tane. Hayır, bir tane çıktı. Ya buna bir tane olmuş. Tam multiple olarak.
böyle düşünüyorum. Ben burada soracağım.
Tam böyle yerim. Tamam. Bugün prodüse konusunda. Bir tane şunun içerisine rahatlık söylüyorum. Lok aldı. Baktı. Motor sıfırda. Yani ne yapacak? Bunu kendisi. Nasıl uyuyor? Şimdi burada zaten lok almıştı. Bunun uyuması demek condition beraberleri uyuyor. Tamam mı? Condition beraberleri uyuyor. Ama Mutex hala uyuyor. Mutex hala uyuyor. Hayır oğlum burada uyuyor, bu da burada uyuyor ya.
O büyümüyor. Bu kurtulma çalıştı. Şimdi bir konser var. Bu da yapıyor.
Hayır oğlum.
Orada da öyle bir sıkıntı oldu. Orada
Şunu yapalım. Oğlum bunun için olmaz. Hatta şu neden buraya var olduğu sorusunda çok kritik bir soru. Direkt sınav konusu olabilir.
şöyle diyorum. Cevabı
Ben de vallahi bir çalışmıştım.
Bu anlatmadan
Lok almaya çalışmış.
alamıyorum.
Şile mi bırakıyorum?
Öyle bir gerçekten.
Var.
Evet.
Böyle inanmasın.
İnanmıyorum.
Gerçekten çok mantıklı.
Kanka, her şey yanıyor.
Okay, so that's the story with the condition variables. It is supported by the Preemptive library, POSIX library, and as you see, it is supposed to be used by the Mutexes because the Mutexes provide the critical region capability. Can I enter the critical region? And I am leaving the critical region thing. Okay, so let's not forget about this thing. When I say that if this condition variable is available, then I will enter this place. If not, then I am not going to enter. And as you see, it takes another parameter, the mutex. Okay, of course, this one and this one are supposed to be the same, right? And again, the same thing here. But when I signal something, condition consumer, I don't see the mutex. Why is the reason? The reason is this. Because if I am blocked here, pthread condition wait, okay, if I am blocked here, I have to release this mutex. If I don't release the mutex, okay, then the consumer cannot enter the critical region. It will be blocked at this point. So this function is smart enough to make this mutex available to the other threads. So when you wait for conditions to happen, you are waiting for two things actually. This condition P is available, somebody signals you, also the mutex is available too. Okay? Two things are supposed to be available, otherwise you cannot continue from this point. Okay, that's the reason this one takes two parameters. If I use only a single parameter like this one, then I would be blocked here, and nobody can enter this to this critical region because I am holding the mutex, and it would be a deadlock because only this process can signal me to wake me up, to wake me up. Okay, so that's the reason we have the second parameter in there. Again, this is not a course about systems programming. We are just trying to tell you what's going on when you do this kind of stuff in the kernel part of the operating system. That's why I'm not going to teach you all kinds of details about this using the Preemptive library to do the multi-threading or multi-processing or process synchronization. We are just trying to give you some ideas about what kind of problems might happen with these kind of ideas. Okay, good. Any questions? No questions. Then I will continue. Writing multi-threaded programs is not an easy thing. It is a very different logic compared to the sequential programs that we have been writing from the beginning. With the sequential programs, if you make a mistake, it is usually easy to find it because you run your program line by line and you trace it. You print out your variables on the screen. Using a debugger, you try to see if the variables are correct values, etc. With the multi-threaded programming, you can't do that much because there is no single program anymore. They are running in parallel, okay? And if you observe an error from your program, that doesn't mean that that error will happen all the time given the same conditions, because of the race conditions, right? Race conditions mean that your output different from time to time. Why? Because of the scheduling decisions done by the operating system. So it is really difficult. It is not that easy. So people thought about this. How can we make this a little bit easier for the programmers? Okay. So they come up with this idea of monitors. Okay, it's going to make our life a little bit easier. It won't be as easy as the sequential programming, but a little bit easier. We will get help from the programming language itself. Okay, so using semaphores and mutexes correctly is difficult. You have to remember about the mutex itself. You have to remember about the condition variable or the semaphore and etc. Okay, and testing is difficult. It is all timing dependent. It is all scheduling dependent. Most of the time it works, sometimes it doesn't work, etc. So we need a higher level construct. For that one, they invented the monitors. Okay, Java has a direct support for this monitor idea. Original C and C++, they don't have this support, but you can get this support easily in other libraries. Okay, so at a higher level, the language itself provides you this capability. The idea of monitor is very simple, actually. Okay, the mutual exclusion part, the programming language handles it. It says that, okay, if you are using a monitor is a special kind of a class or a special kind of a function or a method, if you like to call it that way. Okay. When you call a method in Java, for example, if it's a synchronized or monitor method, only one thread can call it at the same time. Okay. If two threads are calling the same method, one of them has to wait. Okay, so the blocking is done automatically. So the blocking is done automatically, and mutual exclusion, you don't have to think about it. So mutexes are automatically solved by Java. That doesn't mean that you don't have to make your own condition variables, etc. Yes, you have to, but at least you don't have to think about the mutual exclusive regions, critical regions, and etc. So the critical region becomes your whole function or whole method. When you call that method, you know that by the compiler, by the guarantees of the compiler, you know that you are in a critical region, and you don't have to talk about the mutexes. Okay, so let's talk about this. Again, we are going to give the same example about producer-consumer problem, and I am going to give you the Java implementation of the producer-consumer using the monitors. And if you remember, those of you who took the object-oriented programming course, there was the object class with a big O at the top of all the Java hierarchies. There were a number of methods inside it, like the toString method or the equals method or hash method, etc. There were two methods like signal and wait. Okay, Java supports this monitor idea from the top of the hierarchy of the Java classes. So any class can behave like a monitor class using those methods, and they can communicate between each other. So Java supports this multi-threading idea. Also, it supports this kind of a communication from the very fundamentals of the language itself. Without talking much, let me give you the idea of a monitor. It's like a class, as I said before. I have my variables inside my class, and I have my condition variables, like remember the producer condition and the consumer condition. Okay, and my procedure producer and my procedure consumer, only one can call these two functions. Nobody else can do that. And this is the idea. Okay, mutual exclusion is done automatically, but again, to communicate with the other threads, I have to use two operations, wait and signal. Wait is for blocking. I am waiting for something to happen. Signal says that, okay, that thing happened, just wake up anybody who's waiting for that, okay? Who's waiting for that, that's the idea. That is the wait and signal methods of the Java object class of the Java hierarchy. This is just a set of code. I am going to skip this set of code, but I will give you the Java implementation of this producer consumer code, okay? So public class producer consumer, okay? I have a static final, okay, this is a constant n. I have a new producer, a new consumer. I have inner classes, producer, consumer, and our monitor, three classes, inner classes, okay? I made three static objects, producer P, consumer C, and our monitor. Monitor is here. So these are two threading classes, okay? I am going to use P and C as our threads, and I'm going to show you how to do that. And this monitor will act as our monitor, and inside the monitor we will have our critical regions. Okay, so this is the main says that, okay, start the producer thread and start the consumer thread. So two threads are running, okay, and our main thread is running here too. This is how you write a Java thread, okay? As I said before, Java supports threading, multi-threading from the core of the language. There is a superclass named thread. If you extend this class, you become another thread class, and all you need to do is you just provide this virtual method, okay, abstract method run. Run is for the producer doing very simple thing. In an infinite loop, it produces an item and inserts the item to the monitor, okay? So if you look at this one, I am not doing anything about the process synchronization. Very abstract code, very nice code, very simple code, okay? Producing an item is, again, let's give the example of printer queue. I produced a file to be printed, and I am asking this monitor to print that file, okay? After that, I will return to the top of the loop and do this in an infinite amount of do this infinitely. Okay, and producing an item is something very simple actually. Okay, that's it. So this is the producer. Consumer is doing just the opposite. It will be exactly the same thing. While loop, it will, okay, let's look at the consumer. This is the consumer static class. Consumer extends thread. And okay, good. Okay, this one extend thread, and item while true removes the item from the monitor and consumes it, and that's it. Okay, the interesting stuff happens inside our monitor. Our monitor is again another static inner class, and it says that I have an integer buffer of size n. N was maybe 100, I don't remember. I have 1, 2, 3 private integers. Count is the number of elements that I have inside this buffer. I'm going to use a circular buffer mechanism in this case, okay? If this is my buffer, okay, this is 0, element number 0, this is element number n minus 1. Low will point to this point, high will point to this point. That means what? That means the place between these two is filled, right? Okay, so this part is filled with the data that needs to be consumed. But as I said, this is a circular buffer. What does that mean? If it's a circular buffer, then I can I can do this kind of a stuff instead of doing this. This can happen too. What am I going to do here? Let me okay, let me read these, this, and this. Yeah. Okay. It could be high is here, and low is here, low. That means what? This part of the memory is full. Okay? So it's a circular. I mean, low is the low part of the one. So when you add something, you add to this end. When you remove something, you remove from this end. Okay? When you are when if high is pointing to this position, then you can wrap around, and high points to this position, and you go it this way. So your item number is usually at the position index modulo size. You can find your item number. So it is a circular buffer thing. You know this from your data structures course. Okay? So it's a very efficient way of using your buffer. You can always add your new items at one end, and you remove your items from the other end. As long as you have as long as the number of items is smaller than the buffer size, you can continue doing this. So that's why I have this. I mean, that's why I have this low index and the high index. Okay, good. So let's look at this method insert. As you see, it is synchronized. Okay, Java keyword synchronized. Synchronized means that it can be called in a mutually exclusive way. It can be called only once. No two threads can call this function at the same time. If they call it, one of them will be blocked. Which one? It is up to the Java scheduler. It is up to the Java thread scheduler. Okay. If one of them is inside this synchronized insert, the other one cannot go in. It will be blocked. So the whole method insert is a critical region. Okay. Similarly, whole method of remove is a critical region. I don't have to think about those anymore. Okay. So mutual exclusion is automatically solved. That's what we are saying. So I can forget about creating a mutex. I don't have to think about making the mutex available to the others. I don't have to think about destroying it, etc. This is all done by the programming language itself, Java itself, by the language itself. Okay, so insert, and it serves a variable. Let's look at this how it is implemented. Okay, so our condition variable. Okay, if count is n, if I have n elements in my buffer, then I need to go to sleep. There is a very simple function, go to sleep. Let's look at that one actually. Go to sleep, it says that just remember the method wait from our object class. Call that wait. Okay. And well, I mean, usually it's a good idea to write a catch statement if it can throw an exception. Okay, sometimes it can throw this exception. It's not a good thing. It throws, then you are in trouble. But I am trying to do this. Okay, try wait. Okay, and then there is a catch statement, and I am not doing anything. In this case, wait didn't work, or there is some problem here. So it's a good idea to do this. But the idea is, you just call wait here. Okay, just call wait here. You say that if count is n, if my buffer is full, I am going to wait. If the buffer is not full, then I am going to put this value inside this high position, and I am going to increment high by 1, but I am going to take the modulo of n. Okay, why? Because I am running this circular buffer, and I am going to increment count by 1. Okay, I am going to increment count by 1. Why? Because I have one more item. And if count is 1, that means what? I had 0 element in my buffer. I added the first one, so I am letting the consumer know that there is an item available now. I am notifying it because the consumer might be sleeping on this condition if count is 0. Okay, I am going to wake them up. Okay, so very similar code to what we did before with the producer consumer done by the condition variables. Remember, in those condition variables we said that if the buffer is not 0, then I am going to block myself with this mutex and etc. Remember, I had to provide both the condition variable and the mutex. In this case, I am just saying wait. I am going to wait. That is, I am going to block myself. Okay, and the remote just does the opposite. It is synchronized again. The whole thing is in a critical region. Value, if my count is 0, there is nothing to consume for me. I will have to wait until somebody wakes me up. And get the value from the low position of the buffer and increment the low position by 1 modulo n because of the circularity. Decrement the count by 1. I removed one of them. And if count is m minus 1, that means what? The buffer was full, but I consumed one of the items. That means that there is one space for the producer to fill in. So I'm going to notify who is waiting for. I'm going to notify everybody waiting for to fill in the available place. Okay, so this is the notify. Okay, so wait and notify works this way in Java, and at the end I am returning the whatever I recovered. So this monitor here, this monitor class, okay, our monitor class handles everything about synchronization, including the mutual exclusion and the condition variables. Our consumer thread and the producer thread are written like regular programs. I am producing something and pushing it down to a buffer, and the consumer says that I am consuming data from a buffer, and they don't talk about any mutexes, they don't talk about any condition variables. Good. What did we say at the beginning? We said that, I mean, this is getting a little bit complicated. Writing programs are difficult. Well, write it this way. Put all those complications in your monitor class like that and make your methods synchronized. Still, you have to solve a few problems and usually copy some code from a well-known program and modify it. And I am not saying that you should be safe after this point, but it's a good starting point to write multi-threaded programs. Of course, this assumes that your programming environment is supporting these monitors. Not all the programming languages support it. C doesn't support it, right? Well, you might say that I can use the Preemptive library. Well, of course you can use it. When you use the Preemptive library, you have to satisfy this the mutual exclusion constraints yourself. I mean, that was the point. Let's forget about the critical regions, and the critical region thing is going to be satisfied by the language. Okay, that's the idea of the monitors. Let me see if I am forgetting anything. Well, yeah, okay. I don't think I forgot. That's good. Okay, they are nice, but they are only available to a few programming languages. Okay. Monitors, semaphores, mutexes are fine on a single machine, even multiprocessor. Okay. Well, for them to work, maybe some shared amount of memory is needed. Well, we solved this problem for threads and the processes too, but how about this? How about this? I have a computer, another computer, and they are connected to a network connection. Okay? So it is difficult to have some shared memory location for these two computers because they are connected over a network. It is difficult to have some sharing data over the network is easy, not that problem, but sharing memory is not that easy. So what am I going to do? I need to find a solution for this kind of my process is running here, my producer is here, my consumer is there, right? How am I going to solve this problem? Let's look at this problem after our discussions of Mutexes, semaphores, condition variables, and monitors. If you don't have any questions, then I'm going to look at this picture now. Yes?
In the previous code example, is there a reason that all the classes were static for producer?
In this Java program, is that the reason for what?
Is there a reason that all the classes were made static? Producer was a public static.
No. Well, why do you make a static class?
I don't know.
What is the meaning of a static class?
One instance of it.
No. You remember it wrong. What is the meaning of a static inner Java class?
To call it in main, maybe?
Anybody remember? Yeah?
It can reach the parents' fields.
It cannot reach the parents' read. I mean, just to prevent it from reaching the parents or the container classes private data or that kind of thing. Because static means that, okay, it is common to whole class. It doesn't have anything to do with the private or public data members. Okay? So the static classes can only see these static data members. Non-static ones, they cannot be reached. So it is, I'm providing another level of privilege. If I remove all those statics, this would work exactly the same. Of course, I cannot remove this main static thing. I mean, it's the same reason why main is static, right? So it has nothing to do with the synchronization. And I think you discussed this in your data structure course. Okay, good. So talking about this, and if there are no questions, then I will continue with this case. Okay. The answer is message passing. Okay. We are going to use our network libraries, network communication libraries, to achieve this process synchronization. With the network libraries, it is possible to send and receive packages from a destination, or send a package to a destination and receive a package from a source. It is possible. That's what we are going to do in this case. Again, consumer producer, and I'm going to give you a simple set of code to do this, and it is as easy as this. Well, since this is set of code, the producer process runs this code in an infinite loop. I produce an item, okay. I receive a package from the consumer first. Interesting. I'm supposed to send something to the consumer, but I am waiting to receive a package from the consumer. Then I put whatever I have produced inside this message. Then I send it to the consumer. So it's kind of, I am waiting for an empty buffer. I get the empty buffer and I send it to the consumer. Very weird solution here. Why do I need to get a new buffer from the consumer? It will be clear in a few minutes when we look at the consumer code. Because we like to, I mean, if I don't do this, this loop will run indefinitely, okay? And it will send millions of packages to the consumer. If the consumer is not ready, then what's going to happen to those packages, okay? The network will be flooded with my packages, and many of them will be dropped, and that's not going to be good. So this is kind of a solution for that problem. Only maybe 100 buffers are available. I can send at most maybe 100 buffers. So this is kind of a solution for that problem. Let's see what the consumer does. Okay, consumer is doing this. Okay, item my message. Before it starts running this infinite loop, it sends an empty packages to the producer. Okay, send an empty. N is of course a finite number, like 10 20, 50, 100, whatever. Okay, so it sends n packages to the producer, then it runs into this loop. It waits for a package to arrive from the producer. It extracts the item from it, and it sends the empty package back to the producer and consumes the item. So overall, there can be, or there is exactly n packages going back and forth between the producer and the consumer. So we solved this problem of millions of packages floating around and jamming my network connections, and I don't know which one is doing what. Okay, so this is kind of a solution for producer consumer over the network if sharing of memory location is not possible. Of course, you could do the same thing on the same machine. You don't need a network. You can run the same model. Then this would be a little bit inefficient because modifying the same memory location is always the most efficient. Okay. Well, I mean that when I say this, send a package or receive a package, these are very complicated procedures actually, because there will be lots of questions about, okay, how about the acknowledgement? How about the flow control? What if my network is flooded? Okay, what happens if something happened to my message and my message is not the same as before it is changed? Is there an error? Can I detect that error? How about this ordering? I mean, with some networks, package number 1 is received before, let's say package number 50 is received before package number 45. So order change and etc. How about authentication? How about the security if somebody is trying to hack my system and etc.? These are all about, okay, your network cores, and we will ignore those. We assume that they all work fine. And with the networks, these are some serious problems, and your packages get lost, because if one of the gateways of your network is full of packages, it will start dropping some of the packages, okay, and it will never let you know that you lost some packages. You are supposed to figure that out, etc. Sometimes you receive 50 packages at a time. Sometimes you have to wait for a long time to receive packages, ordering and etc. We ignored all of them. Again, these are all about networking, and you will deal with these kind of problems with your networking course. Okay, good. Any questions on this? So we looked at 3 cases. Okay, the memory is shared, and memory is kind of shared with the processor, and memory is not shared. So we are mostly concerned about when the memory is shared, because that's where the race conditions are. We need to deal with the race conditions to make it work the way that we want. Okay, any questions so far? It looks like I am out of the material for about the process synchronization, inter-process communication. Now we are going to start talking about scheduling. Okay? Scheduling is decision of who is going to run next. Okay? I have several processes runnable. They are waiting in the, remember at the beginning of the chapter, there was a talk about, can I do this? 20? There was this, yeah, this one. Okay? So my processes could be either running or ready or blocked. If I have a single CPU, only one process can run. And many processes could be waiting in the ready queue, and many processes could be waiting in the blocked queue. Okay? So maybe this is not a queue, right? Maybe this is not a good idea to write a queue there, because maybe blocked set is good. Because there is no queue in the block set, there is no ordering. Whoever is becoming ready, they just put into the ready queue. Ready becomes a queue, because when you come into the queue, you will be put at the end of the queue, depending on the scheduling decision. So which one would you choose out of this ready queue? Of course, you would say that the first one. But how would you form this queue then? I mean, if you are putting the first one into the first, that's first come, first served basis scheduling. Yeah, well, that's a scheduling idea. But sometimes you don't want those kind of scheduling systems. I mean, you don't want to do first come, first served kind of scheduling. Sometimes you like to change the order. That's the idea of the scheduling. Let me go back to my slide. So scheduling is making this decision. Who is going to run next out of all the ready processes or the threads if you are scheduling threads? Okay. So the answer is, of course, it depends what kind of system you have. If you are in a batch system, okay, if you are in an old batch system, the first generation computers, there is no scheduling because there is only one task available and it is running, right? If it has to wait, it has to wait. Maybe you could say that, okay, when that program is done, who is going to run next? Well, since we didn't have an operating system for the first generation computers, who is going to run next will be decided by the operator, who is the person, the human operator that is running the whole computer. So the scheduler in that case is the person who loaded the card deck onto the tape, right? That was the scheduler. Maybe that person loaded his friends' programs before the other people's programs. So your friendship is kind of making some sense in that case. But later, when the batch system started it started being supported by the operating systems, somebody has to make a decision. They realize that, okay, if I am running, okay, if I am running processes that are both I/O intensive, that means like this one runs and it just blocks. It spends lots of time blocking. Okay, why? Because it is waiting for keyboard input output, mouse movement, etc. or something, printing something to the screen, then runs and then again blocks, waiting for something from the desk, and runs, and so it spends most of its time waiting something for something to happen. Our interactive processes are like this. Usually, our interactive processes, usually they don't do much. Think about the Unix terminal. Okay, it doesn't do much, it just waits for you to type something. Okay, and most of the time it is just blocked. But these are called I/O bound processes. And there are other types of processes. These are called CPU bound processes. When they take the control of the CPU, they just keep using it. They are rarely blocked. These kind of processes are usually numerical calculation processes, for example. Okay, I am trying to calculate the 1 billionth digit of the number pi. Okay, or I am trying to calculate the gene sequencing of for some kind of an animal or whatever. I don't need much. I don't need to do some kind of an I/O. I just keep using the CPU. That's what I have. These are CPU bound processes, and we usually, when we do the scheduling, we usually favor these kind of processes. We say that maybe these interactive processes should have a higher priority than this one. So the schedule this one before this one. Why? Because I know that this one is going to release the CPU in a very short amount of time. It will wait. While it is waiting, okay, I'm going to let this process run. That's a better usage of the CPU time. Also, since these are interactive, I won't make my customers wait for long. Okay, so it was the since the initial time. Okay, give priority short time sharing requests. Okay, so the time sharing requests are given higher priority, and interestingly, the third generation computers, they say that who is a time sharing, who is an interactive process. I don't know which one is an interactive process. How would you know that there is an interactive process? They say that I am going to measure the number of keyboard clicks. Okay, let's say I have 3 processes running, P1, P2, and P3. I don't know which one is interactive, and the thing is that sometimes this one becomes interactive, sometimes this one becomes interactive. It takes a few inputs from the user, and it makes lots of calculations, then it becomes interactive again. So how am I going to do this decision then? Somebody had this idea. Let's measure the number of keyboard pushes. If somebody is interacting with the process, there is lots of keyboard input. I would measure it, and so I would give my priority to those processes. And people figure this out, and they say that, okay, I sit here while my program runs, and I keep pressing the space button all the time, once every second. That will make my program run a lot faster, because the operating system thinks that my process is an interactive process, and in fact it is not. So these kind of things can still happen, but that's the idea. Even today, we must give priority to interactive processes. Interaction is one of the main, for some systems, maybe the main motivation. For example, interaction is number 2 priority for this computer. Okay, maybe the number 1 is the battery management, because if the battery is dead, then that is the meaning of the interaction. Okay, so for this kind of computer, interaction is important. For this kind of computer, interaction is maybe not as important as that one, but it is important. But for the batch systems, interaction is not that important. So what I'm saying is that your scheduling, the question is, who is going to run next? Depends on your environment. Okay? And we are going to choose our scheduling algorithms, or design our scheduling algorithms, by looking at what am I doing, by answering this question. Okay? So this kind of analysis we are going to do a lot in our case. Okay, we know this, our process behavior. Okay, process, again, assuming that we have a single CPU. Okay, processes alternate using the CPU with the I/O request. Some of them use the I/O a lot, some of them not much. And we like to make this distinction between the CPU-bound processes and the I/O bound processes, and usually we favor the I/O bound processes over the CPU bound processes in terms of scheduling. That's the idea. And when do we make a scheduling decision? Okay, well, after a fork, when you do the fork in Unix, okay, I have a single CPU. Who's going to run now? Okay, am I going to run the parent? Am I going to run the child? Okay, that's one scheduling decision for you. Okay, if a process voluntarily terminates itself, who is going to run next? When a process blocks, who is going to run next? I need to make this decision. When an I/O completes, hard disk says that I completed this I/O, the data is ready, I am causing this interrupt. As an operating system, I handle that interrupt. Now my scheduler has to make a decision. Who is going to run next? The interrupted process or the process that asks for the data? Okay, and sometimes, maybe importantly, after timer interrupt happened, who is going to run next now? I mean, is the interrupted process going to run, or maybe I should say that's enough for you, I am going to run some other process? Okay, so these are the all times where you need to make a scheduling decision. Okay, maybe related to this one, sometimes after the timer interrupts, let's look at this concept of preemptive versus non-preemptive scheduling. Okay, for the non-preemptive schedulers, okay, timer interrupts are not the reason, cannot be the reason to switch from one process to another one. Non-preemptive schedulers lets a process run as long as it wants. Okay, so if I take the CPU and if I run this loop in a non-preemptive scheduler environment, this will run infinitely. Operating system will not take control of the CPU, and no other process will use the CPU, because this is a very CPU bound process doing nothing but spinning. And since my operating system scheduler is non-preemptive, it just doesn't stop me from whatever I am doing. Okay, there are these kind of schedulers. Okay, there are these kind of schedulers. For example, a batch system could be programmed this way, or very, very primitive operating systems, they run this way. And the initial versions of Windows, actually, they used to run this way. Once, if a program crashes and it runs into this kind of a loop for some reason, and most of the time it used to kill the whole operating system. Okay, so as opposed to preemptive systems, preemptive scheduler, they say that after some quantum time is the allowed amount of time that you can use the CPU. After time is up, timer interrupt will happen. Operating system will handle the interrupt, and it will realize that the quantum time is up, and it will switch to another process, and it will block you. Those are called preemptive systems. Most of our modern operating systems, Windows, Unix, Linux, our desktop operating systems, they are all preemptive. Okay, I mean, if a process wants to use the CPU 100% of the time like that, it's not going to kill our whole operating system. It's going to load the CPU a lot, but that's not a threat for our operating system, because operating system is preemptive. My computer will stay interactive, and I can run some other programs as efficiently. Okay, so that's the distinction between preemptive and non-preemptive schedulers. And of course, for the preemptive schedulers, you need hardware help. If there is no timer, if there is no clock hardware available for you, then there is no timer interrupt, and there is no timer interrupt, there is no preemption. Okay, so I need to have a clock interrupt. Having a clock interrupt occur at the end of the time interval to give control of the CPU back to the scheduler. Remember, interrupts are always handled by the operating system. Once the operating system has the control of the CPU, the scheduler can do whatever they want. Okay, good. So we started talking about the scheduling, and the rest of this chapter is about scheduling, and we will talk about it for different environments. For real-time systems, scheduling is very, very different than the interactive systems. For real-time systems, scheduling is this: it is 100 milliseconds for you, and 100 is for you, and 100 is for you. That's it. Can I have 150? No. I am going to use 80% of that time. Can other processes use the rest of it? No. Okay, it is always that way. So it is also strict. Okay, not less, not more, because there are reasons for it. But for the interactive systems, I mean, whoever is more interactive, I like to give more priority to it, etc. So it depends on what kind of environment we are running, what kind of computer operating system we have. That's going to be the idea. Good. Are there any questions? Then I will stop at this point, and I will see you on Monday.
Hocam ben imza atmadım. Nasıl geçti anlamadım ama işte.
Sordum ben dersin
Hocam
başında.
elimi kaldırıp görmediniz. Ben de bölmek istemedim.